Okay, so our next and last speaker for today is Michael Cohen, and he'll tell us about Ramanujan graphs in polynomial time.
Yep. So I just want to warn that I am not really going to be emphasizing my actual contribution here, but more talking about the algorithm for computing Ramanujan graphs in general. Most of this is due to the paper by Marcus, Spielman, and Shrivastava. Anyway, so just a quick reminder of what Ramanujan graphs are and like the old results. Okay, so the most classic version of Ramanujan graphs are deregular graphs, and we sort of look at two separate cases, bipartite graphs and non-bipartite graphs, in which all of the non-trivial eigenvalues, and the definition of non-trivial is exclude the eigenvalue containing the all ones vector, all the vertices for non-bipartite graphs, and then you include there are two trivial eigenvalues of that sort to remove for bipartite graphs, which is the main difference. All of them are at most this certain threshold, 2 square root d minus 1 in magnitude. And so this is the best possible constraint you can impose on the eigenvalues, at least asymptotically. The best possible constraint you can impose that doesn't depend on n. So these are in some sense the best possible spectral expanders. So they were originally demonstrated to exist using some crazy number theory. And that's why they're called Ramanujan graphs. It comes from crazy stuff invented by Ramanujan. And they had both bipartite and non-bipartite versions pretty quickly. And these constructions are also really good because they're what are called explicit. So not only can you write down the whole graph in polynomial time, you can look at any neighborhood of the graph. You can basically deal with an exponentially large graph and look at the neighborhoods of vertices as well. So it's sort of the best possible thing you can hope for computationally. They're basically just formulas to compute the neighbors. It's all great Cayley graphs, whatever. And the main downside is that these only existed for certain degrees. And furthermore, for each degree, they only existed for certain sizes. So you couldn't get Ramanujan graphs all over the place, only in these fairly restricted environments based on primes and prime powers and whatever. Okay, so these basic types of things were the only Ramanujan graphs known for several decades until these new papers by Marcus, Spielman, and Shrivastava. So there are two papers, actually. And they're both based on this same basic technique called interlacing families. So neither of them actually included a polynomial time algorithm when they were written. But they're similar in some ways, different in others. So both of them also only produce bipartite Ramanujan graphs rather than arbitrary Ramanujan graphs. And this is due to a certain technical difficulty with the interlacing families method, which is that basically it lets you bound one eigenvalue of the resulting matrix. So you can bound the max eigenvalue or the min eigenvalue, but you can't bound both. But the great property of bipartite graphs, which is that their eigenvalue spectrum is symmetric. So if you bound the max eigenvalue, you automatically bound the min eigenvalue. And so it lets you cheat, basically. So it lets you do something you shouldn't be allowed to do. But because we can't do what we really want to do, we can't get non-bipartite Ramanujan graphs with this method at all, as far as we know. Okay, so the first paper could produce Ramanujan graphs of all possible degrees, but it had only give you a restricted set of sizes, basically powers of 2 times some constant. And the reason why is it was based on these things called graph lifts. So you repeatedly place vertices with pairs of vertices, so you double size the graph each time. It's a nice thing. And their thing was basically based in some sense on looking at random lifts. There's some subtlety here with this interlacing family stuff. Saying that it's based on the random process of random lifts is not the same thing as saying they actually proved that a random lift is Ramanujan. They absolutely did not prove that, and that's, I've heard, probably not even true. And this involves polynomials show up in this thing, and I'll get into how polynomials show up a little bit later. The polynomials that appeared in this argument were things called matching polynomials, and very sadly, matching polynomials in general are known to be sharply hard to compute. So that means there seems to be very little hope for this construction of Ramanujan lifts of general graphs to be findable in general using their method. Okay, so their other paper, their second paper on Ramanujan graphs also uses interlacing families, but it produces a graph of a bipartite graph of an arbitrary degree in size, or any size that's possible, even numbers. So rather than repeatedly lifting, it just builds a graph in one go. And in this case, the random process that you look at, instead of being take an existing graph and lift it in a random way, it's just take a set of D random perfect matchings, perfect bipartite matchings, combine them, get a graph. Again, this is not actually saying that this random process gives you a Ramanujan graph, but it's sort of implicit in the analysis that you're doing this. Okay. Then also, after that second paper came out, another group of authors gave a really nice result that's a common generalization of both. So basically, they can show you can get graph lifts of arbitrary size, and so a set of random bipartite matchings, D random bipartite matchings, can be thought of as taking a graph lift of the graph of two vertices connected by D parallel edges. So and then take an n lift of that. So that that construction, random lifts of arbitrary size, being Ramanujan, generalizes both, and they use some methods from both papers, come out of like some crazy representation theory. Anyway, so I'm going to be focusing on this MSS4 paper because that's the one that we actually can make. That actually ends up being algorithmic. Okay, so the main result is that there exists a deterministic algorithm that, given a degree and a size, outputs so this is a deterministic polynomial time algorithm, which, given a degree and a size, actually outputs a Ramanujan graph of that degree and that size. This is polynomial in the degree and the size. So again, this is not an explicit algorithm of the sort of the original ones. You can't actually query a neighborhood of a vertex. You only have access, you can only write down the whole graph, and in fact, the polynomial is rather bad as well. So this is basically, so there's an algorithm that was implicit. Like all of these interlacing family papers turn out to have an algorithm implicitly associated with them in some sense. But the algorithm is not necessarily clearly implementable in polynomial time. And this is basically just demonstrating that it is implementable. And I'll get into what that means in a little bit. Okay. So what is this like? What is the basic approach of all of these MSS papers? So basically, they have some random process. This is where the kind of random process of things like combined random, D-random bipartite matchings come out. They have some kind of random process, and they compute or bound the max root of the expected characteristic polynomial of the graphs produced by this random process. And then they show that these sets of characteristic polynomials associated with all the graphs are being grouped into something called an interlacing family. And I'll get into what that is. It's a special property of, like, you can think of it as a property of a probability distribution of polynomials or a family of polynomials. And this interlacing family property guarantees that if the expected characteristic polynomial has a small max root, then there must exist one actual concrete representative of this probability distribution whose characteristic polynomial has a small max root. Okay. So to motivate what an interlacing family is, first I have to sort of motivate interlacing. Why does the interlacing show up? What is interlacing, actually? So first thing to note is average of polynomials is a kind of strange object. Right? So averaging the polynomials and averaging the roots are, in general, very, very different things. And it's not very easy to predict what happens to the roots of a polynomial, even real-rooted polynomials, when we average them in general. But if you have polynomials that have, quote, common interlacing, if you have, let's say, any set of polynomials that all have common interlacing, and you take a convex combination of them, then the roots move in a very well-controlled way. In particular, every root must, so if you look at the kth root, it could be the last root in this case, but you actually pick any k. The kth root always ends up in somewhere in the span of the kth roots of the polynomials you sought, somewhere between the smallest kth root of the polynomials you averaged and the largest kth root. It can never move out of the domain of the polynomials you're averaging, no matter how you're averaging. So common interlacing here just means that when the first polynomial comes in, like basically you see all of the first roots of all the polynomials before all of the second roots, before all of the third roots. You never see the second root of one polynomial strictly before the first root of another and things like that. Okay, so that in turn implies that you can sort of separate out the roots. So basically there's an easy structural way to, once you have this, to actually prove this lemma, to prove that the roots can't escape, which is you can kind of think of these, there are regions where roots are forbidden, right? Anywhere between like the last first root and the first second root can't have any roots, no matter where you average it, because it has the same sign in every polynomial. And so once you have these regions with no roots, you average them all. So you know basically, because you know where the roots are, you also know where the roots are, more or less. You also know where the signs of the polynomials where the roots are. So there has to, you see a plus changes to a minus, must be a root. Anyway, okay. So, wait, did I skip something? Oh, yeah, okay. So interlacing families are kind of a generalization or an extension of a set of polynomials with a common interlacing. So in this case, we actually look at a tree where every node of the tree is labeled with a polynomial. And all these polynomials are required to be monic and of the same degree and real rooted. And, okay, so then every internal node, so a node that's not a leaf, has some set of children. And every internal node is required to be some kind of weighted average, some kind of convex combination of its children. And the children of any given node, any pair of siblings, are required to have a common interlacing. So this is actually a natural definition because it gives rise to a natural algorithm, which you can call the interlacing family algorithm. So the interlacing family algorithm, which you can also just know as a distance proof, but it walks down the tree and it finds a leaf where the polynomial's root is bounded by the corresponding root of the head of the tree. Or you could say the root of the tree, but I want to avoid that because it's kind of a roots. Okay, so the algorithm is very simple. You have a current node at any given time, and the current node starts at the head of the tree. And then you look at all of your children, you write down their polynomials, you take their max roots, or kth roots in general, and you say which one has the smallest kth root, and then you make that your new current node. So you always walk down the tree, and eventually, assuming the tree has bounded depth, you will eventually hit a leaf, and then you just return that leaf. Okay, so why does this work? Why are you actually, so it's clear that it returns a leaf, but why is that leaf guaranteed to have a smaller max root? Well, the max root of the current polynomial decreases monotonically. And this follows from the interlacing lemma that I presented before. Because your max root must be somewhere in the span of the max roots of the children, so if you pick the smallest, it must be less than yours. Okay, so the number of steps is clearly bounded by the depth of the tree, because you always descend by one. And what each step actually requires doing is you have to be able to enumerate your children, and then you have to compute the corresponding polynomial of each of the children, and finally you have to find or estimate the max root for those polynomials, or compare them somehow. So basically all of these steps are usually easy for most of these natural families, except oddly for the compute the polynomials part. So importantly, like the first two interlacing families papers, the first one on Ramanujan graphs by graph lifts, and the second one on the Caddis-Singer problem, which turned out to use basically the same interlacing family as each other. So their polynomials are sort of include matching polynomials as a special case, and matching polynomials are known to be hard to compute. So basically, there's no hope for being able to compute being able to at least to exactly compute the corresponding polynomial at an arbitrary position on the interlacing family tree. And until this work, there was no known way to compute the corresponding polynomials for the MSS4 paper, the other Ramanujan thing either. That's basically what I do. It's also worth noting, by the way, that there is an MSS3, which has not yet been published, but that's restricted invertibility. That one, it turns out, the set of polynomials are naturally easy to compute. So there actually were already known examples where interlacing families were computationally easy, just nothing that gave Ramanujan graphs. Okay, so what's our actual interlacing family? How do we go from this thing of picking random perfect matchings to a tree form like that? Well, okay, so the leaves of our tree, we want them to be the things we end up returning at the end, so they should basically correspond to graphs. But rather than a leaf corresponding just to a graph, it's going to correspond to a specific realization of a graph as a union of D bipartite matchings. Okay, and so yeah, a leaf is that an internal node corresponds to, you've partially determined, so you've determined some of the matchings, let's say the first matching, and then there is optionally one matching that you've only partially determined. So basically, you can commit to one edge in the matching, then another edge, and you're always committing to one edge at a time. And in particular, you commit to matching. It doesn't really matter, but just to sort of arbitrarily specify it, we can say you commit to matching the first vertex on like the left side of the bipartition, then the second vertex, et cetera. You match them in order, and you match them to whatever they get matched with. Okay. So the polynomial is just set to basically the expected characteristic polynomial of all sets of random matchings consistent with the choices you've already made over your remaining randomness. So basically, you're choosing your randomness one edge at a time, and you're looking at your expected characteristic polynomials. Okay. Turns out, basically due to stuff that was already shown in the MSS4 paper, their lemmas were already sufficient to show that this is an interlacing family. It turns out this isn't quite the interlacing family that they used. Theirs was exponentially deep, so it's not suitable for a polynomial time algorithm, but it's basically the same as what they use, and it follows from their lemmas. Now, very nicely, the expected characteristic polynomial, the thing at the head of the tree, is also exactly the same as theirs. So we don't have to do any computations separately from theirs. They already proved it, so you can completely black box that claim that the expected characteristic polynomial has a good max root. Okay, so all you need to be able to show then is that for the interlacing family that I defined, you can actually compute the polynomials, what the expected characteristic polynomials subject to these partially determined matchings. This is really not obvious. Okay. So first of all, what is like an expected characteristic polynomial of a random or of a graph with like some partially determined matchings plus some random matchings? What is this formally doing? Well, so first of all, the graphs we're looking at are always bipartite. So that's the same thing as saying the adjacency matrix can be written in the form 0 as a block matrix, 0, m, m transpose 0. Okay, so it turns out characteristic polynomial of this is basically just a linear substitution, replacing like an x with an x squared of the characteristic polynomial of m transpose. So it turns out it's more convenient, or m transpose m. It turns out it's more convenient to look at that. So then we want to look at m transpose m, and we want to look at the characteristic polynomial of that. Where m is your original matrix, which corresponds to the matchings that you've already determined, or the edges that you've already determined, plus something that fills in the partially computed matching, a random matrix that fills in partially computed matching, which is a partial permutation matrix on a submatrix, plus a random permutation on just full random permutations for each of the missing complete matches that you need to do. Okay, so it turns out very nicely, the original MSS paper showed this fairly general type of, quote, quadrature result, which says that the fact that these are permutations, which are sort of nasty and discrete and care about, seemingly basis dependent and whatever, actually doesn't matter if you just more or less replace these modulo like the expected value. If you more or less just replace these with random orthogonal matrices, and you replace the random permutation on a submatrix with a random orthogonal matrix on a submatrix, you get basically is equivalent. You can basically do the same thing. Okay, so now what we want to do is basically take a matrix, add some random orthogonal matrices with one of them on a subblock, and then we want to be able to compute what is the expected characteristic polynomial of A transpose A. Kind of complicated problem. Okay, the simpler case is where everything you're adding where you're just adding a certain number of random orthogonal matrices in the whole matrix. So this is the case where all of the matchings are fully specified. And there's an even simpler case, which is we just want to know what happens if we add one matching. So that's the same thing as saying we want to add one random orthogonal matrix. So it turns out another paper by MSS, the one that came just before that one, basically defines something that generalizes this type of thing, which they call a finite free convolution. And it turns out the finite free convolution is just a linear transformation of the coefficients of the characteristic polynomial of A. So if you know the characteristic polynomial of A, you can just write it down. Then you can immediately get the expected characteristic polynomial doing very little work. And because this operation is linear, that means if you do it more than once, the linearity of expectation means that like the expected doesn't really matter, and you just can iterate this linear transformation. And so that means you actually have the ability to compute the expected characteristic polynomial from adding any number of random permutation matrices sort of in one go without doing much work. Okay? Then you can also use that same method to remove the dependence on any actual like full matchings that are missing. So you only need to consider the case where there is a partial matching, basically where all you have to do is complete one last matching. That's the only case you need to do that's not covered by the existing MSS stuff. So you might try to hope that this would still be doable as some kind of linear transformation on the coefficients of the characteristic polynomial, but it sort of clearly can't because the actual answer, the actual expected characteristic polynomial, depends on the choice of the submatrix. What are the missing, basically which vertices still need to be matched? And that's not a function of only the eigenvectors and eigenvalues, so it can't be a function of only the characteristic polynomial. So you might think this is the end of your hope, but it turns out there are things that look like characteristic polynomials that have more information. In particular, we can just write down a horrible-looking determinant of a thing that depends on 3 variables, not just 1. So now this has like n cubed coefficients, and these extra variables make it depend on things. Then you just then basically the coefficients of this have all the information you need, and it's linear again, and it's basically just like the previous case. The only thing is this polynomial is a little bit more expensive to compute because it has 3 variables that can, and the degree can range up to n. The proof is elementary. Okay, yeah, I guess that's what I got. Okay, yeah, so this is just some overproblems. So if you actually go through, because of things like the fact that this polynomial is trivariate, there's a bunch of factors of n that add up, and the runtime ends up being something like n to the 5 dense matrix multiplications, kind of crappy. So is there any way to speed it up? I don't know any of the ways to, I don't know any way to get better than that. So another question is, basically like, this is maybe some motivation for these interlacing families maybe not being as nasty and non-algorithmic as people thought. What are some other problems that you could hope to solve with this? Is there any way to get back to normal graph lifts that doesn't involve introducing horrible matching polynomials? Or any other way to get rid of this annoying multi-graph thing that edges can be repeated, which is due to not being a graph lift? Is there any way to, either using interlacing families or not, somehow get non-bipartite Ramanujan graphs outside the range of the original number theory constructions? And also just in general, what other methods for finding Ramanujan graphs are floating out there other than interlacing families and number theory? Are these really the only ones? Some people conjecture that like half of all random graphs are Ramanujan or something like that. No one really knows how to prove it, but that would be certainly a great thing to prove. Yeah.
Okay, questions?
Yeah. It's not really standard. Oh yeah, one thing I forgot to mention. So apparently, so Nishith Vishnoi actually independently discovered basically the same result, and I think he has some more general theory for like what kinds of expected determinants you can get by writing down multivariate polynomials like this. But I don't actually know the details. But as far as I know, prior to people asking this question about the Ramanujan graphs, no one looked at things like that I know of. Yeah, and then this was generalized to k-lifts by that. It does not. And again, so you sort of can't hope to make that result algorithmic by doing anything of this sort, because the polynomials there in the interlacing family tree are matching polynomials, and they're known to be sharply hard. Here, we're solving the problem just by explicitly computing the polynomials exactly, and we know we can't do that. Maybe there are more sophisticated things, like approximating the polynomials. People have thought about that. No one succeeded. But this sort of brute force approach of just do it will not work.